right, great. So welcome to session 9B, ML Security 3. My name is Yisrael Amirsky. I'm a faculty member at Ben Gurion University in Israel. And in this session, we're going to hear some amazing advancements in the domains of database privacy, intrusion detection, and the usability of security. Our first speaker is Chitrabhanu Gupta. He is a PhD candidate at the University of California, Davis. He'll present private aggregate queries to untrusted databases. Let's welcome the speaker to the stage.
Hello, everyone. So I'm Chitrabhanu Gupta, and I'll be presenting our work, Private Aggregate Queries to Untrusted Databases. So as we know, aggregate queries are quite common in a number of different statistical analysis and also in our everyday lives. Suppose a user were to query a medical database to find out the number of patients who have cancer who are also smokers, or they query a social media platform such as X to track the popularity of a specific politician or a set of politicians affiliated with a specific political party. I'm sure a lot of us here in this room have probably recently queried a flights database to find the ticket prices of round-trip flights to and from San Diego. For each of the queries that I just mentioned, if the database owner were to be observing the rows in the database that we are interested in, they're most likely to be able to find out potentially sensitive information about the user and also profile us accordingly with malicious intent in mind. Private information retrieval, or PIR, is a cryptographic primitive that empowers a user to privately query untrusted databases like these, where the database owner is capable of observing all the queries that are made to the database and also can observe all the computations that happen on the database servers. However, there is a dearth in the intersection of solutions that support aggregations and expressive queries with constraints such as searching and sorting, as opposed to positional queries, which are more common in some of the older works. Query speed and efficiency, and also the correctness of response being guaranteed through the queries. So we propose a novel information theoretic PIR or ITPIR scheme that can support aggregations for expressive queries with a number of constraints such as searching and sorting, and is also quite efficient and scalable. Our protocol is a multi-server scheme that can support collusion of up to a certain threshold number of servers. So our protocol is based on the vector matrix model of ITPIR, where the database is modeled as an R cross S matrix, where R is the number of rows in the database and S is the number of columns. And in this model, the query is modeled as a 1 cross R vector with a 1 in the position corresponding to the index of the row in the database that we are trying to fetch. The product of this query vector and the database matrix would normally return the record that we are interested in, but this scheme can be tweaked to produce aggregate queries or aggregations across different rows in the database by introducing multiple ones, as you can see in the diagram here, in the query vector, and then multiplying that query vector with the database matrix, resulting in an aggregation of records in the corresponding indices where the ones are in the query vector. So, however, as is obvious from this process is not private, and so we need to introduce something such as linear secret sharing to introduce privacy to this procedure. So, instead of sharing the client query with a single copy of the database matrix, we first make a number of copies of the database matrix and host a copy each on a number of different database servers. We then use Shamir secret sharing to split the client query into a number of secret share vectors which are of the same dimension as the original client query. And each secret share vector is then shared with a different database server. The underlying idea behind this approach is to pass a polynomial through a secret value that we are trying to hide and extract a number of different points from that polynomial and operate on those points instead. The user will perform component-wise reconstruction once they receive the products of the secret share vectors and the copies of the databases from each of the servers to produce another polynomial which they will then evaluate at the original point to obtain the desired result that they're trying to fetch through their query. In our protocol, we introduce a new data structure called indexes of aggregate queries that maps the database matrix into another matrix which is designed to serve specific queries. In the indexes of aggregate queries, each row corresponds to a unique value of a specific attribute from the database matrix, which in the case of this example here is the patient ID attribute. And each column of the indexes of aggregate queries, which is PyPatient here, by the way, corresponds to a row in the database matrix D. And in this example, we can see that in the first row of the database matrix, the patient corresponding to the patient ID attribute is patient 1, and that is reflected in the first column of the index of aggregate queries PyPatient. Similarly, the second row in the database matrix D corresponds to patient 2, and that is also reflected in the second column of the index of aggregate queries PyPatient, and so on. Multiple such indexes of queries, which are of the same dimensions, can be batched together using a process called polynomial batch coding, which entails constructing polynomials at every index of the indexes of queries using the points at the same indices across all the matrices. Let's now walk through a sample query to understand how the protocol works end-to-end. Let's try to find out the total hospitalization duration of patient 1 in our sample database D. In order to obtain the aggregated result for this query, the first step is to construct a query vector. However, the query vector here would be of a dimension equal to the number of rows in the index of queries matrix as opposed to the number of rows in the actual database matrix as is prevalent in vanilla vector matrix model-based ITPIRs. So in our case, this would be a 1x4 vector because we have 4 rows in the indexes of queries in our sample index of queries. And we put a 1 in the position of the value of the attribute that we are interested in as a search term for our query. Now, we take the query itself, the query vector itself, and as I mentioned earlier, we split it into a number of secret shares using Shamir secret sharing, and the number of secret shares should be equal to the number of servers, which for the sake of this example is 3. So each of these secret shares of the client query are then sent to a different server hosting a copy of the database matrix. Now let's look at what happens on each server. In addition to hosting a copy of the database on every server, we now also host a copy of the index of aggregate queries or the batched index of aggregate queries, depending on the setup for our production database. The secret share of the query vector is multiplied with the index of aggregate queries first. So this results in a multiplication of a 1x vector with a 4x6 matrix in this example, resulting in producing a 1x6 vector, which is then multiplied with the copy of the database matrix, which here is a 6x6 matrix, and that gives us a 1x6 vector. Now this 1x6 vector that is produced at each server is not the result that we are looking for. It is a secret share of the result that is returned to the user. So now let's zoom out and look at what the entire protocol looks like. So the user collects all the secret shares of the result from all of the servers and uses them to reconstruct a polynomial component-wise, and then evaluates the polynomial at the original point of the query to obtain the result, which is the aggregation of row 1 and row 4 that we were trying to obtain. In order to assess the functionality and the potential for real-world deployment of our protocol, we performed a number of case studies. We designed these 2 case studies, the first of which entailed scraping about 1 million tweets from X, which were relevant to the US elections. And using this data set, we constructed a couple of indexes of queries which were batched, and the dimension of these indexes of queries were about 0.3 million cross 1 million, and each row in these indexes of queries corresponded to a unique user ID or like a Twitter handle from the data set. And this batched indexes of queries was used to serve a set of queries around the US elections. Similarly, in our second case study, we used an open source medical data set, Mimic3, to compile our own data set that we used to produce 2 sets of batched indexes of queries, the first one being of a 4 cross around 60,000 in dimension, and the second one being a little larger at 1,400 cross about 4 million in dimension. And in the first one, each row corresponded to a different admission type or nature of admission for the patients, and the second one is bigger because it's at a patient level. These were some of the sample queries that we tested. So for the X case study, we tried out different queries that involve aggregations and constraints around like counts, retweets, and the user IDs. And for the medical data set, we tried queries which have aggregations and constraints around various fields such as admission type, ethnicity of patients, patients in general, and also things like drug dosage and duration of hospitalization. So the detailed results of all our case studies are available in our paper, but I will bring up the case study results for our medical data set based on Mimic3 to highlight a few key features of our protocol. So the first thing to note here is that in case of a real-world deployment of our protocol, the index generation time, the index generation and the batching of the multiple indexes are going to be only one-time efforts, and so these steps are not required to be performed every time you run the same query. So, and even in that case, we can see that the order of time required for these steps are not significant. The index generation time, even for generating an index of order 1,400 cross 4 million, is at most a second or 2, and the batching time for multiple indices is trivial throughout. In our case, we also have to store these indexes of matrices on the server, so we also wanted to track the additional data structure storage size, and it tends to be in the order of MBs even for pretty big indexes of queries. And the VSPM throughput on the GPU, which is the next column, is not very important here because it's basically to track whether the sub-step of multiplying the secret shares of the query vectors with the indexes of queries is a bottleneck for our protocol, and we have extensive benchmarking done around this, and we have that reported in the paper in detail as well, if you're more curious about those. Which brings us to the final sets of columns, which are the server response generation times, and this is what we were primarily the most interested in. So we compared our protocol with a baseline protocol, which is the popularly used Goldberg's ITPIR scheme, which is also a vanilla vector matrix model-based ITPIR scheme. And right off the bat, we can see even the first column, all attributes, refers to a naive aggregation of the records using our protocol, where we aggregate every column in the records that we are trying to aggregate. And even in that case, our protocol performs at least as well as the baseline. And when we use a process which is not as naive and we aggregate only the essential columns that we are interested in, our protocol comfortably outperforms the baseline. Another thing to note here is that our protocol guarantees a single round of interaction between the client and the servers to produce the results, which is not the case for the baseline that we are comparing against and a lot of the contemporary work around ITPIR schemes that are out there. Because in most cases, especially for the positional query schemes, most ITPIR schemes would require multiple rounds of interaction between clients and servers to produce the final result. And that would end up resulting in a total server response generation time that is a multiple of the times reported for the baselines here. Also, we wanted to see how well our model scales for larger databases. And in order to assess that, we took our tweets database and the medical database and enhanced the individual records in both the database to produce two sets of databases of size 40 gigabytes and 64 gigabytes. And we observed that for databases this big, our protocol, when implemented with modular arithmetic with a modulus size of 8-bit or 16-bit, our protocol comfortably outperforms the baseline and reports the results in only a matter of seconds. And the takeaways for in summary, the takeaways for our protocol is that we develop a novel framework that can augment the conventional ITPIR protocols, like the baseline that we compared against, to support aggregate queries with single round of interactions. And we achieve this through the introduction of a novel data structure called the indexes of aggregate queries. And we also simulate a number of real-world applications that help us benchmark the performance of our protocol and assess the scalability and real-world deployability of our proposed PIR scheme for realistic aggregate queries. And finally, we also measure the framework on GPU compute, and we observe that it can achieve very fast query response times while also assuring the privacy and the correctness of the aggregate queries. Thank you.
We have time for one question. Any questions? All right, so I have a question. So first of all, it was a really nice talk, thank you.
Thank you.
I noticed there was really, really impressive speeds in the time to generate those indexes. I was wondering how that scales up to databases with millions or tens of millions of records. Is it linear? Is it?
Yeah, so we do see it is linear. So we actually have, so I didn't go over some of the benchmarking results that we have in our paper, and we actually test exactly what you're talking about. And we do find that it's almost linear, the way it scales. Like we see basically a linear drop in the time as the number of records increase. But we also see that for all practical purposes, the times that we observe are still quite impressive, for at least for the index generation. And again, the other thing is we did encounter a few cases where the index generation was somewhat slower. But the thing is, again, like, these are going to be one-time efforts, right? The index generation, you only generate the index the first time, and then like, you know, if you have a database deployed in production and you have automated queries that generate results every day, like a daily run in the morning or something like that, only the first time is going to be a little bit slower for generating indexes. After that, that time is not factored in.
Thank you.
Yeah.
Let's thank the speaker one more time.
Yeah.